Welcome back to First Principles Daily, episode 14. Closing the week with one more look at where the next 10x is hiding. In the 1850s, aluminum cost more than gold at the table of Napoleon III because no one could separate it cheaply from its oxide. A small bar of the metal occupied the center of the emperor's most exclusive dinner service. Guests of lesser rank received plates of gold instead. Aluminum is the most common element in the Earth's crust, yet at that moment it behaved like one of the rarest substances on the market. Within 30 years, the same metal would be sold by the ton for ordinary cookware and structural parts. Two young chemists reached that outcome by asking what the raw material itself actually required rather than how existing furnaces had always operated. Before 1886, aluminum came from chemical reduction methods that treated the metal as a laboratory curiosity rather than an industrial product. The usual route started with aluminum chloride and tried to displace the metal using potassium or sodium. Those two elements were themselves costly to prepare in pure form, and each batch demanded careful handling of reactive intermediates. Output stayed at a few kilograms per run because the chemistry stayed locked inside small vessels. Engineers accepted the approach because it copied earlier techniques for isolating other reactive metals. No one saw a reason to question the underlying steps when the results matched what prior practice had produced. The finished price reflected that acceptance. Aluminum sold for roughly the same amount per kilogram as silver and sometimes exceeded the price of gold. The market treated the difficulty of extraction as an immutable property of the element. Capital equipment remained modest because output remained modest, and the high price in turn justified keeping output modest. A self-reinforcing loop kept aluminum a symbol of wealth rather than a structural material. Charles Martin Hall and Paul Héroult each began by asking what the theoretical minimum cost of aluminum would be if the only expense were the energy needed to break the aluminum-oxygen bond. The magic wand estimate starts with alumina itself, the oxide already refined from bauxite. Bauxite was abundant, and the bare process for producing alumina was already known, so the commodity value of alumina stayed low. Adding the cost of the carbon anode consumed in the cell and the cryolite flux that dissolves the alumina yields a raw material floor on the order of a few dollars per kilogram, even in 1880s prices. The actual market price sat many times higher than that floor. The idiot index therefore measured in the hundreds and at times the low thousands. That ratio showed that the dominant cost was not the atoms, but the method used to free them. The electrolytic cell dissolved alumina in molten cryolite at roughly 960 degrees Celsius and passed a direct current through the melt. Oxygen reacted with the carbon anode to form carbon dioxide, while aluminum collected at the cathode. Because the process ran continuously rather than in small batches, the energy input per kilogram dropped sharply once cheap electricity became available. Smelters were therefore sited beside large hydroelectric plants where power could be purchased at a fraction of the price charged in cities. The same insight also removed entire categories of equipment. No longer were sodium or potassium metals required as reductants, and the need for repeated filtrations and washings disappeared. Each of those eliminations lowered both direct material losses and the labor hours embedded in every kilogram. The idiot index began its long descent as soon as the first commercial cells operated at scale. By the early 20th century, the price of aluminum had fallen by more than 99% from its 1850s levels. The metal moved from jewelry to cookware and eventually to aircraft skins. The new idiot index, while still above the theoretical floor set by electricity and alumina, was now measured in single digits rather than thousands for the most efficient smelters. The remaining gap is dominated by the cost of continuous electric power and by the capital required to build and maintain large reduction cells. Those constraints are physical rather than conventional. No redesign of the cell chemistry can eliminate the thermodynamic minimum energy needed to split alumina. Later improvements, such as pre-baked anodes and point feeders, have narrowed the gap further, Yet the fundamental dependence on inexpensive electricity remains the binding limit. A material whose market price greatly exceeds the cost of its constituent atoms is announcing a process problem rather than a scarcity problem. The useful question is therefore not how to obtain more of the element, but how to lower the energy and equipment required to free it. The same logic now points toward other oxides and compounds whose current prices still sit far above their material floors. The aluminum story shows that a high idiot index is not a verdict on the element itself. It is a signal that the separation method still carries unnecessary steps whose costs can be stripped away once the physics of the bond is examined directly. Hall and Heroult did not invent aluminum or discover bauxite. They simply refused to accept that the existing chemical route defined the lowest possible cost. That refusal turned a metal priced like a precious stone into one priced like a commodity within a single generation. The same pattern appears whenever a finished price rests on inherited process choices, rather than on the atoms and the energy required to rearrange them. The remaining cost of aluminum is now set by electricity and cell capital, not by any shortage of the raw oxide. Other oxides still priced far above their theoretical minimum are therefore carrying an open invitation to repeat the same examination. Which of those gaps will close next when someone redraws the process from the atoms upward? That's a wrap on today's first principles breakdown. The ideas travel further when you pass them on. Send this to a fellow builder. I'm Patrick in Vancouver. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network, links in the show notes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.
I'm about to prove